Hello, this is Team 6 of Fall 2024 ECE Senior Design 2 at Clemson University. Our project is on the Advanced Driver Assistance System ADAS integration device. And my name is Jane Zhao.
I'm Josh Benson.
I'm John Bedger.
I'm Eric Nielsen.
And I'm Jake Anthony.
Advanced driver assistance systems have rapidly become more commonplace in the automobile market in the last decade. In an effort to make the roadways more safe and allow drivers to have more information about their surroundings, plenty of new ADAS features have found their way into vehicles, such as collision detection, lane keeping, blind spot detection, automatic braking, and reverse cameras. Our goal was to design an ADAS system that could be integrated into older vehicles on the market, such as used vehicles or even newer vehicles that are lacking some of these features. The objectives of our project was to develop a DIY ADAS system for under $500. We wanted to make a backup camera that runs at 80% object detection accuracy at 30 FPS within 25 feet. We wanted to have 2 side cameras for blind spot detection at these same metrics within 100 feet. We also wanted 2 LiDARs to support with the blind spot detection system, and we wanted them to have 90% object detection accuracy within 50 milliseconds and within 10 meters. And finally, we wanted to have a GUI system to display all of this object detection information along with other vehicle information such as RPM, miles per hour, and some other OBD2 available data.
Here we have the block diagram that shows the overarching system that's integrated within the vehicle, and that includes the subsystems with their physical location and their communication protocol. So here we can see the 2 CSI cameras that are connected to the Jetson Nano via CSI. And then we have the backup camera on the bottom there that's connected via USB. And then we also have the 2 LiDAR sensors connected to the sides of the vehicle, and those are connected to the Raspberry Pi Pico via I2C. Also connected to the Raspberry Pi Pico is the reverse gear via a hardware tap, as well as the turn signals via 2 limit switches. And that data gets sent into the Jetson Nano for the Jetson Nano to process that and send that data onto the screen to be displayed to the driver. We also get data from the ECU, the car's ECU, from the OBD2 port via USB.
Here you can see the prototypes for our physical mountings to the car. Everything mounted to the car is attached with double-sided Velcro tape. For our cameras, there is a camera under each side mirror that can be adjusted by turning it on the Velcro, as well as by tightening and untightening some fastening screws to act as a hinge. Our LiDARs are attached in a very similar way, but lower on the door, and also have a screw hinge mount to allow them to point more inward or more outward as necessary. We also have a GUI display screen that's sitting right in the middle of the dash so that the user can see all of the information about the vehicle, as well as the different camera feeds and alerts that will show up when an object is detected. You can also see in the lower part of the screen our backup camera mount that sits just underneath the trunk. And you can also see in the bottom left and right our electrical box to hold all of the internal sensors and wires necessary to connect to the camera's LiDARs and the display screen.
So the next thing is the software flowchart. So the software consists of 3 subsystems. All 3 subsystems start when the car is started. First is the GUI subsystem, which starts on the small monitor in the car and reads in the OBD data, which is speed and RPM. It then enters its main screen where that is displayed, and then it waits for signals from the other subsystems. The camera starts on the Jetson Nano by reading in all 3 camera streams, and then it processes them using the YOLO V5 detection algorithm. If an object is detected, we need to run it through a crash detection algorithm that we made in order to determine its threat factor. Once the camera subsystem marks it as a threat, it checks the LiDAR subsystem. The LiDAR sensor subsystem starts by reading in the LiDAR data and through the Raspberry Pi Pico. That data is then sent into the Nano to be processed to determine if an object is too close. If both the LiDAR and the camera subsystem detect an object in the blind spot, then a warning needs to be sent to the GUI subsystem. If the user doesn't have their blinkers on, a warning light is just displayed. If the blinkers are on, the light comes on, and a noise is played to further warn the user.
And this is the graphic user interface dashboard view, what kind of when the program first loads, what the user sees. So in this main screen, what user get to see are the 2 information comes from the OBD2. First being the speed shown on the left, and other being the RPM shown on the right. And on the left, right bottom corner, you see there's a little red indication symbol. That indicates that there's something in the blind spot, and that's one indication showing that, hey, there's something in the blind spot, you should be careful. And when the user turns on the left or right blinker, it will open the corresponding camera view, a live camera feed showing the vehicle and wherever the camera sees. And if in that camera view, and by running through the algorithm that we had shown in the past, if it detects something in the blind spot, then it will start and play a beeping sound, go beep 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 beep, to let you know that there's something in the blind spot and you should be careful while turning. And overall, this kind of just the only way we provide the user to kind of see if there's something in their blind spot or if there's not something in their blind spot, so that we can provide them and making sure that they can drive safely.
Here we have our electrical wiring diagram. On the right side of the diagram, you can see our buck converter. It takes in the car's 12 to 14 volt battery voltage and steps it down to 5 volts to be used by the LiDARs. In the middle of the diagram, you can see the Pico on the breadboard. And on the left side of the diagram, you can see our left and right LiDAR respectively. Both LiDARs take in 5 volts and ground, and their clock and signal lines meet and share the same I2C bus on the Pico, as you can see in the top right corner of the Pico. In the bottom middle of the diagram, you can see our 2 limit switches. These are attached to the car's turn signal shaft, and they are used to detect when the left or right blinker are turned on. Finally, we have our car reverse signal, which is also 12 to 14 volts, being fed into an opto isolator, and that is being read by the Pico.
So in conclusion, we managed to accomplish what we set out to do, but with sadly decreased range and FPS. Our project met our budget of being under $500. We were able to consistently detect objects in our blind spot within 5 meters and at 5 FPS, and with a resolution of 960 by 540 pixels. Here are our acknowledgements and references. Now we are going to cut to a live demonstration video. Okay, so in this first clip, we start off on the backup camera when we're going in reverse. And then we switch to the main screen of the GUI where you can see the speed in miles per hour and the RPM as we're going forward. And then we are about to make a turn here. So you see the side camera open up. In this next clip, you're about to see a light come up on the left because we detect a car. And you'll see I try and open the feed to get the sound to come up, but I did it too late, unfortunately. In this clip, we detect a car on the right side, and I quickly open up the camera feed, and you can hear it. And in this last clip, we're just going to park. And as we drive by the cars in the parking lot, you can hear the audio warning and the visual warning on the GUI.